Okay, we have already seen some tests to determine the convergence or divergence of a given series. Today we talk about more tests. In particular, we talk about comparison tests. We have a comparison test and also we have a limit comparison test. So let's first talk about the comparison test. And for the comparison test, we only deal with the series with positive terms. So let me lay out the comparison test. So let sigma n could run from any integer to infinity, and sigma bn be two series with positive terms. And suppose term by term, an is smaller than bn. Suppose for every n, an is less than or equal to bn. Now, if we know that sigma bn, the series with larger terms, is convergent, then sigma an is also convergent. So if we know that the series with larger terms is a convergent series, we can conclude the term with the series with the smaller terms is also convergent. To clarify this, let's see some examples. Use the comparison tests to determine the convergence or divergence of sigma of 1 over 3 n squared plus 5. Do you know a series that we already know about the convergence and divergence of that, and it has some similarity with this series? You remember, so when I want to solve this, I see that I have n squared at the bottom. On the top, I have 1. So let's look at the series of 1 over n squared and compare that series that we are given to this series. So we know that this is from the previous lesson. This is convergent, right? Why is it convergent? As a reminder, it's a p series with p equals 2. You know that if p is more than 1, the p series is convergent. Now, term by term, for every n, no matter what n is, 1 over 3n squared plus 5 is less than or equal 1 over n squared. Why is it true? They have the same numerator, but the denominator of the fraction on the left is larger, which makes the fraction on the left smaller. So if we have two fractions we want to compare, if they have the same numerator and the denominator of one of them is larger, then the fraction with the larger denominator is smaller. So here we have this. Therefore, by the comparison test, therefore, by the comparison test, sigma of 1 over 3n squared plus 5 n rounds from 1 to infinity is convergent to. So by using comparison test, comparing with sigma of 1 over n squared, we conclude that this given series is also convergent. Let's see another example. Determine the convergence or divergence of sigma 1 over n to the power of 3 over 2 plus 1 as n rounds from 1 to infinity. I would suggest that you pause the video and try this on your own, and then compare your answer, your solution to my solution. So I know that sigma of 1 over n to the power of 3 halves plus 1, excuse me, without plus 1, just 1 over n to the power of 3 halves is convergent. This is why, because it's a p series with p equals 3 halves, and we know that if p is more than 1, that we mentioned that here, the p series is convergent, similar to the previous example that p was 2 and 2 was more than 1. And term by term for every n, one over n to the power of 3 halves plus 1 is less than or equal 1 over n to the power of 3 halves. Therefore, by the comparison test, sigma of 1 over n to the power of 3 halves plus 1 is convergent to. Okay. Okay. Let me also mention the limit comparison test, which is a little bit different from comparison test. Here again, we have two series. Let sigma of an and sigma of bn be two series with positive terms. As the name suggests, here we find the limit, but the limit of what? The limit of the general terms. Let the limit of an over bn as n tends to infinity be L, where L is neither 0 or infinity. So L is a number, but it's not 0, a number different from 0. If this happens, if the limits of the ratio of the general terms of the two series is a number other than 0, of course, it cannot be infinity, as it's not supposed to be infinity, then either both series converge or both series diverge. So if the limit of the ratio of two series, the general terms of two series, is a number, a finite number, different from 0, then the nature of these two series in terms of convergence and divergence will be the same, meaning that either both converge or both diverge. Let's see an example here. Using the limit comparison test, determine the convergence or divergence of sigma of k to the 4 plus 2 over k to the 5 plus 1 as k runs from 1 to infinity. Which series would you compare this limit-wise? So suppose this is the general term of this. I use k, so instead of a n, I have ak. What series do you consider to compare limit-wise with this series? Since we are comparing the ratio of the two series, we should be focusing on the degrees of the top and the bottom of the general term. On the top, the degree is 4, at the bottom, degree is 5. So the difference of the degrees is 1. Do you know any simple series that the difference of the degrees is 1, that the top is 1 degree less than the bottom? That is sigma of 1 over k. Why I use 1 over k? Because the top is 1 is of degree 0, k is just k is of degree 1, so the difference of the degrees is 1. The bottom has a degree 1 unit more than the degree of the top. And this is in fact our bk. Again, in the statement of the comparison test, I used n, but it could be any other letter. In this example, it's k. So first of all, when I compute the limit as n tends to infinity of ak, since it was not nk in this example, let me use k here, of bk. So let's do this limit. K tends to infinity. Ak is what? K to the 4 plus 2 over k to the 5 plus 1. Bk is what? 1 over k. Let's simplify this fraction using basic algebra. So k times k to the 4 plus 2 goes to the top. The product of these two is k to the 5 plus 2k. And the product of these two goes to the bottom, which is k to the 5 plus 1. As we have done this before in the discussion of the limits of sequences, to find this limit as k tends to infinity, since k tends to infinity, we can keep the term with the highest term from the top, and the term with the highest power from the top, and the term with the highest power from the bottom. And k to the 5 or k to the 5 is 1, so the limit is 1. So we can use the limit comparison test. Since the limit of the ratio of the general terms of these two series is a number neither 0 or infinity, so the limit is 1, is neither 0 or infinity, then sigma of k to the 4 plus 2 over k 5 plus 1 in terms of convergent or divergent is like sigma of 1 over k. But do you remember sigma of 1 over k was harmonic series and was divergent? So this is divergent too. This is divergent. Remember that sigma of 1 over k is divergent. It's a p series with p equals 1, and we know if p is less than or equal to 1, the p series is divergent. The other way we verified the divergence of sigma 1 over k was by the integral test. So use the limit comparison test to determine convergence or divergence of sigma of 1 over radical k to the 5 minus 2k plus 10 as k rounds from 1 to infinity. So which series do you compare to this series? This is a little bit tricky. So we compare it limit-wise. Of course, I'm using the limit comparison test. Under the radical, I have k to the 5 minus 2k plus 10. Since for the convergence or divergence of series, it matters for the large k's, so we can ignore minus 2k plus 10 to obtain this series. So if I assume that this is what I have here is a k, the series that I would consider is 1 over square root of k to the 5. And this is the general term of bk. By the way, this is the same as sigma of 1 over, using algebra, k to the power of 5 over 2. And this is a p-series with p equals, so this is convergence. Why is it convergent? Because it's a p-series with p equals 5 over 2, which is more than 1. It remains to find the limit of the ratio of the general terms of these two series as k tends to infinity of ak, which is 1 over radical k to the 5 minus 2k plus 10 over 1 over radical k to the 5. Simplifying this fraction, radical k to the 5 goes to the top, and radical k to the 5 minus 2k plus 10 goes to the bottom. Both the top and the bottom have radicals, so I can think of one big radical, k to the 5 over k to the 5 minus 2k plus 10. Again, since k tends to infinity, for that fraction under the radical, I can keep the term with the highest power on the top and the highest power at the bottom. But k to the 5 over k to the 5 is 1. Let me simplify this as 1. And radical 1 equals 1. So again, I got some number, some finite number, different from 0. Therefore, by the limit comparison test, this series is also convergent. The series that I compared limit-wise with, sigma of 1 over radical k to the 5, is convergent because it's a p-series with p more than 1. Therefore, this series is also convergent. So let me write the conclusion in the next page. Therefore, sigma of 1 over this series that we dealt with, radical k to the 5 minus 2k plus 10 is convergent to, just by the limit comparison, by the limit comparison test.